1.
Hello and welcome to today's webcast. It's hip to be square, new modular rectangular HDPE stormwater management systems, sponsored by Uponor Infra. My name is Alana Maya. I'm the assistant editor for Waterworld magazine, and I'll be your moderator today. A few housekeeping items before we begin. The slides for today's presentation will be pushed to your screen automatically. A PDF of those slides is available in the Event Resources tab in the console window. This presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. If you're running pop-up blocking software, you'll need to disable it to view this webcast. In addition, it's recommended that you close all other applications for better performance. If you have any technical difficulty during the webcast, please type your issue into the Ask a Question box, and a member of our webcast support team will work with you to correct the problem. A certificate of attendance will be issued automatically via email to all attendees at the conclusion of the presentation. Just please be sure to stay logged into the webcast until you see the congratulations message. For your convenience, this presentation will be available on demand within 24 hours of the live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at waterworld.com. We have two presenters for you today. Grant Thornley is the Director of NA Sales for Uponor Infra. With 25 years of experience in the industrial, municipal, and power markets, Grant's area of expertise is in pipeline infrastructure rehabilitation, asset management, stormwater and wastewater management, water transmission, and condition assessment. Brian McGuire is PE Manager for North American Engineered Systems for Uponor Infra. Brian McGuire is the Manager of Uponor Infra North America Engineered Systems portfolio. He oversees product development, sales, marketing, engineering, and operations related to Uponor's engineered system portfolio throughout North America and is a licensed professional civil water resource engineer with over 20 years of experience in the civil construction materials industry. We have a quick survey before we begin, and you should be getting that now. Once you complete that survey, I will turn the presentation over to Grant.
Hello.
And I will turn the presentation over to Grant now.
Good morning. Thank you very much for everyone attending today. We're looking forward to a great presentation today. And thank you for Penwell and Elena for hosting this. To start on today's topic of the agenda, for today's webcast, Brian and myself will be focusing and introducing you to our new Weholite modular stormwater management system. The Weholite stormwater modular system was born out of about 50 years of our HDPE experience and requests from our clients looking for new ways to save time and money for installations and or rehabilitation of their stormwater systems. I thought we'd start off today with me providing everyone with a kind of a quick overview of Uponor Infra, what our products and systems we offer, and then quickly touch on the benefits of HDPE. Afterwards, Brian will be doing a deeper dive into our Weholite modular offerings and how our systems address quantity and quality, configuration of our systems, engineering design considerations, and lastly, which I find exciting, a review of our test barrel unit, which we just conducted up in Huntsville this year. So to start, who are we? Well, Uponor started out in about 1918 as a furniture manufacturer of all things. We branched out later. I mean, how do we get from manufacturing furniture to HDPE? Well, if you hold on, I'll take you through it. The manufacturing of furniture kind of quickly turned to beds. In the beds, there was metal bed springs. So to help facilitate that, they purchased a forge in which to make those bed springs. Later, the forge was expanded in around 1946 to produce cast iron pipes, just due to the infrastructure demand in World War II. Metal in Europe became more expensive, so materials, more innovative materials were thought out, and Uponor began manufacturing PVC piping. Later on, advancements, like anything, material sciences advanced, polymer science advanced, and Uponor began manufacturing PEX piping, which offered our clients, particularly in the residential commercial market piping areas, less expensive piping than copper, and provided longer life and easier installation. In 1999, we continued to expand out globally, and in 2013, we purchased a company called KWH. And one of the manufacturers Uponor partnered with, which is KWH, it allowed us to leverage our knowledge and strengths from both of these companies in structural HDPE and manufacturing. On a global basis, Uponor is a publicly traded company with net sales of 1.1 million euros or 1.5 million Canadian, depending on the exchange rate of the day. 1918, Uponor has grown internationally. We now have over 3,900 employees. We comprise of 3 different divisions. Infrastructure Solutions is really who manufactures the Weholite stormwater systems. We also have plumbing solutions and indoor climate controls. Uponor globally also helps to support our local engineering groups in areas of R&D, FEA analysis, and project review and design. On more of a local level for North America, Uponor operates several offices located throughout the U.S. and Canada. Formerly, much of our business in North America was conducted under the name of KWH, which you may know us by, but in 2013, the name was changed to Uponor Infra, and that's how we're now recognized in North America. We've been manufacturing HDPE since 1967, so actually this year we'll be celebrating our 50th anniversary of HDPE manufacturing. Some of you may be familiar with some of our trade name products such as Sclairpipe, Wehogas, Weholite, and Wehopanel. Those are our main trades. All of our manufacturing facilities are ISO 9001-2008 certified. Our products and systems we have certified to many standards such as NSF, CSA, FM, B&Q, ASTM, and others. Since we manufacture and support systems right across North America, it's important to have those certifications. Our head office is in Mississauga in Ontario. Is responsible for day-to-day project design, modeling, FEA analysis, 2D design, as well as support to our custom fabrication. As well, in addition, Brian heads up a lot of our FEA analysis and design as well. Some of our retention-detention systems, just a quick collage of some of the systems we see. I won't go into it, but you can say we have barrel system designs, and what we'll be talking today is the modular design. So quickly, since a lot of you probably already know what HDPE is, but just to touch on why HDPE is part of the resin properties. The resin used to make Weholite pipe and Wehopanel have long-term properties. The 2 main properties critical in establishing the long-term life expectancy of a 100-year design for it is stress rating, the maximum stress levels that can be sustained for a period of 50 years, and also slow crack growth resistance. The other aspect for HDPE, if you ever have a chance to see it on site, it's very smooth internally and externally. And the mannings, which we term as the manning number, this is the friction between a pipe surface and the water flowing next to it. The different piping materials have different friction factors in the mannings number. Concrete's initial value is 0.001, whereas HDPE has a significantly lower number. What this means is that I can have a smaller diameter pipe for the same flow as something as a concrete pipe. So by using a smaller pipe, I can actually reduce my costs but maintain my same flows. Concrete versus flexible pipe, and I bring up concrete because that's probably much one of the main things we see in the industry, which is slowly changing to more polymer solutions. You can kind of see this is kind of a standard photo on the left. You can see it's a photo taken from the American Concrete Pipe Association, basically promoting the virtues of rigid concrete pipe. You can see a bunch of people and sacks weighted on top of this pipe. It points out that the primary feature of the concrete pipe, and that's really it supports a lot of weight. The rigid pipe design approach is well accepted design method. But today's pipes are designed using flexible pipe approach, uses the surrounding soil of buried pipe to provide some structural support to the pipe, whereas concrete provides all of the structural support and can be buried very close to the surface. What flexible pipe does, it uses the interactions with the soil to provide additional support. And by using the flexible pipe to interact with surrounding soils, we benefit by having a pipe capable of addressing developed stresses resulting from misinstallation, which is a big one, rather than developing pinpoint stresses or developing stress fractures or shear cracks in pipe, which are sitting on top of rocks. The actual HDPE pipe can bend around that. It can also address seismic concerns, particularly on the west coast. That's one of the biggest issues or design things that we have to consider. And also allows us a system that's less expensive than concrete, since we're using the free surrounding earth to help with our designs. To further, just to touch on that a little bit more, both rigid and flexible pipe design methods work. Like anything, is that there is no panacea or one solution fits all. But in cases where you're burying pipe, HDPE is a very good option. The rigid pipe, with help of surrounding soil, has sufficient strength to carry imposed loads. Flexible pipe is deflected and mobilize sufficient soil support to carry imposed loads. Deflection of pipe is typically equalized. You can see in this picture around the radial pressures acting inwards and loaded like a compression ring. Failed conditions, when you kind of see on the concrete pipe, because it can't flex and use the surrounding soil, it has to take the entire load, illustrates a failure. And this occurs when the imposed live load or dead loading conditions are exceeded. So just a quick overview of the difference between flexible and rigid pipe. The other aspect for HDPE and why it is one of the reasons the important characteristic of HDPE is one that benefits is the inertness of the material and allows us to promote and design to a 100-year design life. Acid and bases commonly cause premature deterioration in stormwater systems, especially concrete, as it dissolves the concrete. Acid and bases can enter a stormwater system by the introduction of fertilizers, industrial soaps, or really any other contaminant that can be flushed down a sewer. Hydrogen sulfide is also a concern. Hydrogen sulfide can cause deterioration of the concrete pipe, particularly at the crown of the pipe, where the hydrogen sulfide is typically present when organics are in the water, whereas HDPE is unaffected by H2S or hydrogen sulfide. Lastly, HDPE is a non-metal, so it doesn't suffer from corrosion mechanisms such as oxidation reactions. Many concrete pipes, such as pre-stressed concrete cylinder pipe or PCCP, have metal wires wrapped around on the inside of the pipe to help strengthen it. The problem occurs over time when these metals corrode and snap. The metal wires lose their integrity. In turn, the entire pipe loses its structural integrity. Another benefit to HDPE is its abrasion resistance. It's able to, when it's impacted, it's able to absorb the energy from particles. So any application where you see particulate or sand, this is the material to use because it reduces abrasion, and that's very common to have sand or particulate in a stormwater sewer system. I'll just leave one other slide before Brian takes over. Is one thing, I was at a conference a year ago, and in their discussions, or one of the presenters, just bringing this up, is that we see a movement in North America move away from conventional materials, and we're seeing HDPE, or even I'm going to say polymer because PVC is there as well, is that polymer pipes and materials are moving up and becoming more recognized and more engaged within municipalities. And that's due to more and more applications being successfully installed and people realizing that the overall operating costs and life cycle costs have dropped significantly. So that being said, I'll hand the presentation now over to Brian.
Well, thank you, Grant, and good morning, everyone, and thank you for coming here today. What I'd like to do now is briefly discuss Weholite and Weholite modular materials, how they're fabricated, and how they can be utilized for a number of different applications. Then we'll speak to stormwater water quality and quantity management and how Weholite modular can be utilized for those applications. We'll briefly cover thermoplastic welding, structural design, and then we'll cap it off with a review of our recent in-field live full-scale load test that we conducted to validate our structural design methodologies. For those that aren't aware, as Grant mentioned, Weholite has been manufactured in North America since 1981. We have been producing ASTM F894 structural profile wall pipe up to 132 inches in diameter in 2 facilities in North America. And in 2013, we actually took that rectangular panel cross-section and utilized it to develop a material we refer to as Wheel panel, or also Weholite modular, our rectangular configuration for structural profile wall systems. Both Weholite and Weholite modular rely on a robust rectangular cross-section, which you can see there. This gives us a double wall profile and allows us to provide both inside and outside extrusion welds to provide an extremely durable system that's ideal for applications where a leak-free system is required, specifically stormwater, wastewater, and potable water applications where zero leakage is acceptable. Weholite and Weholite modular are ideal solutions for those applications. Here you can see a snapshot of a 132-inch diameter Weholite vessel being extruded in a spiral wound configuration in our Huntsville manufacturing facility with our quality control inspectors. You can see in that photo the individual stripes represent the individual rectangular profiles and the extrusion weld between them. Similarly, we can extrude panels of material in our Wheel panel and then use those flat sheets of material to create rectangular structures, bulkheads, baffle walls, anything you can imagine. What Uponor endeavors to do is we take our Weholite and Wheel panel materials and combine those with thermoplastic fabrication and fusion welding, which we'll talk a little bit about later, to create a host of applications for the water, wastewater, and stormwater space. Essentially anything you can think of where the pumping, treatment, or storage of water is required. We can manufacture a custom-engineered solution that not only provides a leak-free solution, but also provides a system that has a 100-year design life and enhanced durability. There are some distinct advantages to Weholite modular, rectangular configuration, 100% polyethylene systems. What most folks would come to conclude is that durability and sustainability are the primary advantages. As I mentioned, we're immune to pH, hydrogen sulfide, and corrosion, can provide a 100-year design life. What most folks also don't know is that polyethylene welds much like steel, and that allows us to design and fabricate almost any configuration necessary to support a project, whether it's internal baffle walls, pumps, controls, instrumentation, suspended solid topper bottoms. We can come up with a design to meet the project needs by custom fabricating all the internal controls and components. We can produce a 100% watertight system and provide field and factory quality control of both the welds and the system itself. Installation is also much faster using Weholite modular. We are 1/10 the weight of concrete, and this allows us to produce much larger structures than we can typically produce and ship in precast concrete. Typically, we can manufacture structures, completely prefabricate all the internal components, deliver them to the job site, have them set, and be ready for plumb and backfill within a matter of hours or days, as opposed to weeks with comparable concrete solutions. And then at the end of it, we can reduce the total project cost by reducing the total number of loads, the size and amount of equipment required on the project, and the total site time to significantly reduce the total project cost and cost of installation of the system using Weholite Modular. So just some advantages to keep in mind as we go through this presentation today. We'll talk about stormwater hydrodynamic separation and filtration. We'll also discuss stormwater detention and how Weholite Modular can be used for those applications. But bear in mind that Weholite Modular can be used for a host of other applications as well, whether it's DSO storage and pumping, rainwater harvest, culvert reline, wastewater treatment, irrigation, custom structures. Anything the engineer may be faced with where the pumping, treatment, or storage of water is required, we typically work with them to develop a custom solution for their particular application and support them with the details necessary. So keep that in mind as we go through the presentation. And some examples of the versatility of the material that are a little bit outside the stormwater quality, quantity, and other boxes that folks might think of. We'll show you some projects here. This is an extremely large, 14-foot high, 50-foot long, total suspended solids baffle wall separation system. This project, in addition to it demonstrating the versatility of the material, also shows you that we can produce much, much larger structures that could normally be accommodated with concrete. And we built this structure in particular with concrete. It would have required multiple loads. If it were precast, if it were cast in place, it would have been an extensive forming and pouring time in the field to create a structure of this magnitude. Alternatively, we can create this structure as one unit with all internal components prefabricated in it, and also quality control tested and leak inspection tested in the factory and in the field to ensure a high-quality leak-free system is achieved. These two photos just demonstrate some more details and applications we can use Weholite Modular. Here on the left-hand side, you see a stormwater outlet control structure that has a polyethylene baffle wall with low-flow controls, access ladder, and inlet port. That particular baffle wall would have to be reinforced to accommodate full hydrostatic pressure differential, or ponded depth on one side and zero ponding on the other. And that's something that the Weholite structural profile allows us to reinforce the annular space to accommodate any loadings we encounter in the field or in design. On the right-hand side, you see a large-scale hydroelectric power plant intake facility that was actually welded in the field to support the magnitude of that project, just demonstrating the versatility of the material. Another project which also demonstrates the versatility of Weholite is what we refer to sometimes this photo as engineered art. This is an above-ground ultraviolet treatment facility for a potable water plant. This particular project required haunch support, as some might conclude. Horizontal pipes full of water require support of the haunches to prevent the pipe from squatting under the weight of water. So we're able to actually use Weo panel to create that haunch support and a base for the system and develop a completely leak-free polyethylene UV treatment system and deliver it to the project ready to be plumbed and brought online. Just another example of the versatility of the material and our ability to support engineers with developing new solutions to old challenges. So what I'd like to do now is branch into some specifics regarding stormwater management, specifically quality management and quantity management, how we use Weholite Modular to meet those challenges. To discuss quality management, we really need to break out hydrodynamic separation and media filtration as two distinct approaches to providing particulate removal, TSS, total suspended solids removal, and total phosphorus, which is usually the nutrient that is tracked in most jurisdictions for nutrient removal. When we speak to hydrodynamic separation, the industry has evolved and jurisdictional authorities have evolved to prefer hydrodynamic separation be utilized for pre-treatment only. It can be used in some jurisdictions as standalone treatment. However, it does not achieve the removal rates that media filtration does, and for that reason, most jurisdictional authorities have relegated hydrodynamic separation for use as pre-treatment, as part of a treatment train to provide trash, debris, and large particulate removal. HDS systems typically remove particles in the range of 125 microns and up. They're typically awarded a 50 to 60% total suspended solids removal and a pretty low 20 to 25% nutrient or total phosphorus removal rating. So when we look at HDS, we should be aware that HDS systems are typically vessel systems, round, cylindrical, vertical vessels, or horizontal systems, vessel systems with baffle walls. So Weholite modular, large-scale rectangular structures are not often going to be cost-effective approaches for the smaller-scale HDS pretreatment units. However, we could use a Weholite modular system and have, for larger-scale total suspended solid sedimentation bays, where you have either large flow rates and or large sediment loads that can't really be accommodated with the smaller scale vessel form hydrodynamic separation system. So on most projects, you're going to look at HDS for the simple round, cylindrical Weholite vessel vertical or horizontal configuration. We can support you with those. But where Weholite modular in this presentation are concerned, and HDS, we would typically be looking at projects that have much higher flow rates and much higher sediment loading, and we'll show you one of those. Where Weholite modular is most appropriate for quality management is in reference to media filtration, particularly sand filters. Sand filters and media filtration remove smaller particulates, typically 50 microns and up, provide a higher level of TSS removal, 85 to 90% TSS, and phosphorus removal rating of about 50 to 60%. Most jurisdictional authorities have standards and specifications. We'll talk a little bit about that in a second for media filtration and sand filters, and recognize them as standalone, high-quality removal systems that can be approved in most jurisdictions. So to speak to, again, hydrodynamic separation using Weholite modular, again, we're not looking at smaller scale, round, vertical or horizontal vessels. We're looking at larger scale systems with high debris loads and high flow rates, where we want to remove large amounts of sediment and or with high flow rates. And Uponor can work directly with the engineer to develop a custom system that uses hopper bottoms, internal baffle walls, and flow controls to remove 50 to 60% total suspended solids, trash, and oil. And you're also going to get that 20 to 25% total phosphorus removal rating. The basics of hydrodynamic separation design go back to Stokes' law. Oops. In the interest of time, I'm not going to go through Stokes' law, but basically what we would do is work with the engineer of record and develop a TSS removal calculation that supports their project based on the most critical design parameter, which would be particle size, and then also flow rate. And then based on our knowledge of the project site, what would be the debris loading for that particular project. And Uponor can support any project where the engineer wants to develop a custom large-scale Weholite modular hydrodynamic separation system in accordance with jurisdictional regulation. Moving along to quality management using media filtration, as we said earlier, sand filtration has been around for a long time, highly tested and validated and improvable by most jurisdictions. And Uponor has taken the approach to adopt local sand filter regulations and design methodology and incorporate those into our Weholite modular system. Where historically sand filters had fallen, or structural sand filters had fallen by the wayside because the size and scale of precast sand filters made them less than cost effective, because we can now build a rectangular vault much larger and more cost effectively using Weholite modular. We're able to build larger sand filters more cost effectively and make them a more viable option for projects. For those that aren't familiar with structural sand filters, it's a fairly simple concept and very easy to maintain. It has an inlet pipe with an energy dissipator and a sedimentation bay that allows for sedimentation, trash, debris to be isolated to the front of the system. It's typically sized to 25% of the water quality volume in that first chamber there on the left. We'll have a baffle wall and then followed by a level spreader to distribute flow across the media bed. And then we'll have a sand filter bed that also has some geotextile and gravel on top to prevent channelization, but also occlusion of the sand media itself and erosion and scour. And basically that sand filter bed area is sized to provide water quality treatment for the flow rate on a given project based on the impervious area and the water quality depth for that particular project. And then finally we have outlet control wall and an outlet control bay that can have low flow discharge to regulate your low flows in accordance with your local regulation. A lot of advantages to using a Weholite modular sand filter One primary advantage is there's over 30 years of in-field operation and testing to validate performance. There are known standards that are established by Corps of Engineers, EPA, NJCAT. Also, most folks aren't aware that sand filters achieve a better performance rating for total phosphorus and suspended solids from most jurisdictions in comparison to proprietary systems. We'll show you an example of that where a sand filter receives a higher removal rating than all proprietary systems in a certain jurisdiction. It has proven performance, and probably more importantly to your owners as you're working through projects, is that sand filters do not require very costly media replacement programs, and they don't lock your owner into replacing media cartridges or media over the life of that system. Most cylindrical canister media filtration systems provided by the proprietary industry require replacement every 1 to 2 years, and each canister typically runs between $200 to $250 per canister. So your owner would then be stuck having to buy canisters, typically at the rate of 10 to 20 canisters per area of acre of impervious area, every 1 to 2 years. And that locks them into a long-term cost and does not allow them the flexibility to switch out their canisters. Their whole entire system is based on a proprietary system. Conversely, with the sand filters, they can locally source sand media anywhere in their area. They can use their own forces to remove the top 2 inches of sand and replace them, or they can subcontract that for a much lower cost. So Uponor has taken this approach to provide media filtration in a non-proprietary media way to free owners of the burden of having to be locked into that long-term proprietary media replacement program associated with proprietary medias. This slide just demonstrates the host of testing and design calculation standards that are out there in the industry. Any one of us can go ahead and Google our jurisdictional authority and type sand filter in after it, and it's likely that you'll find a standard in your area, but it'll all link back to Darcy's law. Here we see, as I mentioned earlier, how sand filters get a higher level of removal rating than most proprietary systems. This is a snapshot of the Virginia DEQ BMP Clearinghouse. It's a program whereby they provide a rating for all proprietary and non-proprietary water quality systems, both above ground and below ground structural BMPs. This particular table demonstrates that the Virginia DEQ only awards a 40 to 50% total phosphorus removal rating to proprietary systems, whereby sand filters get a 60 to 65% total phosphorus removal rating with the Virginia DEQ, who is a recognized authority in the world of stormwater quality management. There are 3 distinct standards that you'll see in jurisdictional authority guidelines regarding sand filter technology. Specifically the Washington, D.C. Underground Sand Filter, Delaware, and Austin Sand Filter. These technologies have been around for over 30 years. However, the D.C. Underground Sand Filter Vault is the structural BMP sand filter you'll see most used. Sand filters are based on Darcy's law, or flow through any media is based on Darcy's law. The reason I have this slide up there is because you'll see some minor variation from one jurisdictional authority to the other on how sand filter surface area is calculated. Some might also change the volume required for the pretreatment bay or the max depth of the media or head over the system, but they all still rely upon the fundamentals of Darcy's law. If you have an understanding of Darcy's law and flow through the media, you'll be able to quickly decipher the jurisdictional authorities' guidelines for sand filter sizing, and it'll become a little bit clearer as you take a look at that. To that effect, the New Jersey Stormwater NJCAT Stormwater Design Manual has sand filter specifications and sizing regulations that are based on a water quality design form where they correlate the water quality flow rate volume to a filter bed area, and that's how that's calculated there. Conversely, we also have the Virginia DEQ, just as an example, where the area of the filter is based on a treatment volume, again, water quality volume. That's your volume of water that requires filtration. Anyway, their surface area is based on that, but again, both of those methodologies link back to Darcy's law. Not to spend too much time getting into sand filter calculations, Uponor will work with the engineer of record, civil engineer, to develop sizing that would work with that particular jurisdiction, whether they were working in Seattle or Ontario or Virginia or Florida. We would look at that jurisdictional authority sizing methodology. We have extensive sand filter sizing calculation tools. We would rely on the civil engineer of record to do the hydrology, to calculate the water quality volume, their channel protection volume, and their low flow water quality flow rates, and their high flow rates. Provide some form of splitting, either a low flow, high flow orifice or weir split prior to the structure. And then we would take that information and then we would design the sand filter based on the local jurisdictional authority requirements, share that with the engineer along with some structural details, specifications and standards for the sand filter so they can incorporate into the plan. So that's the level of support we provide engineers, recognizing that many engineers do not have structural design capabilities or sand filter design capabilities. We're here to help them get through and give them the tools and resources they need so they can support their owners with a non-proprietary system. Here you see a snapshot of a Weholite modular sand filter drawing. It's a very simple bill of materials, identifies all the components inside the system. Again, you saw this slide earlier here where we talk about the fundamental components that would be incorporated into any sand filter. So this is a good basis of what most sand filters would look like. If they needed to get larger, we could also link multiple units together to create much larger sand filters as required for a given project. So with that, I'm ready to transition into quantity management and storage. Where quantity management is concerned, we don't discuss it here in this presentation because this is a Weholite modular rectangular discussion. However, Uponor does manufacture large manifold storage structures using large diameter pipe up to 132 inches in round pipe with prefabricated manifolds to connect them hydraulically. When you're talking quantity management and storing large quantities of water below ground for peak flow attenuation, round pipe is almost always going to be your more cost-effective approach. So when we're looking at a project and supporting an engineer, the first place we'll look is, can we get a round configuration to fit within the available footprint on that project? Because if we can, that's going to be more cost-effective. However, if existing site conditions, building location, road, existing utilities or proposed utilities, or other features on the project significantly limit the footprint to make round infeasible, then we can look at doing a rectangular Weholite modular detention structure. It will be slightly more costly than a round system. However, the benefits of reducing the footprint can also sometimes reduce the backfill, excavation cost, and disturbance on other parts of the site that may make that additional cost to do modular detention worthwhile for the project. And we can look at both round and rectangular. This is a snapshot of just a simple rectangular Weholite modular quantity management system. This one would just be a single structure. We can incorporate outlet control baffle wall with low flow, mid flow, high flow weirs, any internal components necessary for the project into that quantity management system, including a confluence with an energy dissipator to bring multiple pipes into, say, a 4-bay inside the structure. We can do that as well with some internal baffle walls. Similarly, we can link multiple Weholite modular structures together hydraulically in what we refer to as a Weholite modular array, where we take multiple structures based on the available hydraulic storage depth on a project, how much ponding can we get without impacting the upstream HDL. That would dictate how much height we have in the system, and then obviously our site footprint would dictate the horizontal configuration. We can typically squeeze much more water in a tighter footprint using a rectangular Weholite modular array than we can with round. Additionally, we don't have the pipe-to-pipe backfill that we would see in a manifold system, so the systems become significantly smaller, and typically a Weholite modular footprint would be about 50% of an equivalent round footprint. So again, round is going to be more cost-effective. However, if you do not have the available footprint, rectangular can often be used to solve those challenges. Here we can see just another snapshot of that array and some detailed plans, and how we handle the hydraulic connectivity between the two vessels in that slide there. So now I'll move on to thermoplastic fusion welding. This is, it could be a very long discussion on thermoplastic fusion welding, but I decided to include this here just so folks have an understanding of thermoplastic fusion welding, and because it is a cornerstone on how we fabricate systems and how we justify the structural design of our systems. Thermoplastic fusion welding should not be confused with techniques such as gluing, brazing, or soldering, which create a seam and do not actually melt the base materials and create a monolithic material. Thermoplastic fusion welding involves heating the base materials A, B, and a filler to prescribed temperature range based on material type and thickness to create a homogeneous weld pool, such that we get molecular alignment of the weld material across that seam, and we don't have a weak point in the structure. As a matter of fact, when we go to do tensile strength tests, that weld should be the strongest part of the system, as we would expect, because it should be a little bit thicker than the rest of the material. And so when we do a tensile strength test, as we'll see in a little bit, the actual profile should fail, not the weld seam. Just to familiarize folks with what extrusion welding is, we actually pass a granulate wheel or wire reel of material through an extrusion chamber, which melts that material and then applies it to the weld with a welding shoe that's sized for the type of weld it is, the geometry, whether it's a 90-degree or a chamfer or butt-end connection. There'll be a specific weld shoe for that. We also heat the base materials with air to get them to the prescribed temperature. So again, heat weld material, bring them to the prescribed temperature, very important. Here you can see a welding technician applying an extrusion weld to the bottom. You can see a dull appearing haze following that weld, which we'll talk about in quality control. There are two standards in America that would be adhered to for thermoplastic fusion welding. Anyone can go buy an extrusion welding gun and weld things in their garage. However, it's important for manufacturers to adopt the standards that are out there, specifically DBS, AWS, and we'll show you ASTM standards as well. DBS is the grandfather of polyethylene welding standards. It's been around for a long time. Their standards are extremely strict, and Uponor adheres to DBS standards. AWS welding recently came online. It's more of a self-certification program or quality control program for the qualifications, procedures, and performance related to thermoplastic welding, and allows manufacturers to fall in line through a sort of self-regulated process under AWS, and Uponor meets both DBS and AWS standards, and any manufacturer who manufactures structural polyethylene systems should. As I mentioned, ASTM standards, there are extensive ASTM standards related to the design and manufacture of structural polyethylene systems, and these standards would apply to Weholite Modular. We won't go through these in detail, but you will hear me mention later ASTM D2321 for installation. When we work with an engineer of record to develop specifications, detail, and design, we will incorporate the necessary standards for his project and give him some boilerplate that he can bring into his specifications. Quality control and assurance is very important where thermoplastic extrusion welding comes into play. Our first line of defense is a visual inspection. As I mentioned earlier, a heat-affected zone should follow the weld seam. This would be a dull-appearing haze or dull-appearing polyethylene as that extrusion gun follows the weld seam. If we see inconsistencies in that haze or splashes of material or shiny spots, we did not get a good weld, and we'll have to regrind and reapply that weld to that particular part until it tests. Pressure test of internal voids is something that's unique to Weholite because we have a hollow annular space that is continuous through most structures. We're able to pressurize that internal void wherever there's a discontinuity, pipe penetration, top slab, or other fabricated element that might penetrate that void. We're able to pressurize that void and confirm that it is leak-free prior to it leaving the facility. And then the last line of defense for quality assurance testing would be, obviously most folks are aware of, infill and exfill testing, or some refer to as 24-hour drawdown testing, in accordance with ASTM 2487, which will fill the structure up and observe leakage rates. Here you can see a snapshot of our pressure test at our facility, where we'll actually drill a hole in the annular space and pressurize it, turn the flow of pressure off, and then observe that it holds pressure, and then certify that. If it does not, we'll have to spray soapy solution, look for leakage in the area wherever that annular continuous profile is, and then regrind and reapply weld before it leaves the facility. It's just part of our quality control and assurance program. Briefly discussing some applications and categories for Weholite modular rectangular structures, just so we can kind of put our minds around some of the things that we have to consider when we're designing a Weholite modular structure. Above ground modular units for wastewater treatments, industrial applications, and sometimes stormwater management applications where they want to have an above ground system, maybe in a landfill application. And then we also have below ground non-vehicular rated, which would account for pedestrian and emergency vehicular load only. And then we have below ground vehicular rated, which is rated to HS25, CO625 rating. Just briefly running through that, for above ground, we'd have to consider the wind load, local building code, also ambient temperature. If we're in the deep south, we have some projects going to the Houston area. We have to account for 110, 120 degree ambient temperature. We also have to be concerned with solar exposure. If we're in an area that could have high solar exposure, we would want some shielding, either with a canopy or with some sort of vinyl cladding or aluminum cladding on the outside of the structure to protect the structure from direct solar radiation. And then obviously hydrostatic head, ponded water elevation, soil bearing, or other components that we'd have to consider for above ground modular. For non-vehicular rated below ground modular units, we'd be concerned with the existing soil bearing and modulus, any existing or proposed utilities. Most non-vehicular loaded, even pedestrian-rated applications will have what's referred to as an emergency vehicular load, which could be a fire truck or a pickup vehicle. We'd need to know what the limitations for that would be. And then obviously the pedestrian loading, typically 300 pounds per square foot, is the design consideration there. And then buoyancy is a subject that comes up from time to time, where we would actually extend the base plate of the structure to capture soil column to increase the amount of soil we capture with the base to counteract buoyancy. If that cannot be sufficient, we would then also add a concrete collar from time to time when we couldn't extend the base plate sufficiently far enough to counteract buoyancy. And then the difference between below ground non-vehicular and vehicular rated is simply in the vehicular classification. All the remaining concerns are the same, but we would need to understand not only the type of vehicular load we're looking at, HS25, CO625, alternate military is sometimes a requirement, and then also what the road alignment and traffic pattern, how many lanes are there, and what is the alignment of the road over top of the structure. And then we would account for that in our structural design, which we'll talk about in a second. So our structural analysis and design methodology is really boiled down to two fundamental programs that we correlate with one another. We utilize a CANDY, which stands for Colder Analysis and Design. It was a program that's been developed back in the 1970s by Dr. Katona out of Dayton University in Ohio to analyze how buried structures interact with the soil in a nonlinear elastic type of model. In that as that soil compacts, stress and strain is alleviated in the soil model, and it comes to some form of homeostasis. It's not necessarily a linear elastic, an elastic relationship between soil structure and load. And Dr. Katona developed the CANDY model to allow us to analyze buried structures. And Uponor will utilize CANDY to evaluate the backfill, subgrade load, and vehicular load over top of structure. We'll show you what that looks like. We also use an Inventor three-dimensional finite element analysis program where we'll build the structure out in 3D, and we'll apply loads to the structure to determine the deflection. We would then correlate the results of both of those, and then, if necessary, apply any reinforcement. That reinforcement could come in the form of just straight polyethylene profile or solid wall polyethylene reinforcement. We can also incorporate steel in the annular space of our profile to further enhance the structural rigidity of the system. So we will run a structural analysis, and then we will go ahead and evaluate the deflections, stress, strain, moment shear, and determine whether or not additional reinforcement is required, and then incorporate that into the structural design. Both methodologies are backed by material testing, full live scale, full load testing we'll talk about at the end of the presentation. and then calibrated with empirical data. We also have third-party validated design methodology. We employ a company known as CBC Engineering that are experts in buried structure design. And we've had them participate and collaborate with us throughout the design and development of our structural design program. We're happy to have them as a partner with respect to Weholite Modular. So this is a snapshot of our Candy model. Candy, as I said, is a 2D planar analysis. It refers to culvert analysis and design. The red section is your existing subgrade, existing soils. The yellow is what we refer to as a non-select fill or class 3 type of material. We have the orange area, which is your select fill, class 1 or class 2. Both yellow and orange areas are compacted to 90%. And then we can apply a vehicular load represented by those red dots and move that vehicular load through increments in the program to determine where the point of max stress strain on the system occurs, and then look at the deformation of the system and whether or not structural reinforcement is required. And we can do this for single-cell, multi-cell systems. And here's a snapshot of our Inventor 3D FEA where we apply loads. You can see there on the outside of that this structure had some reinforcing beams on the exterior, and we were able to design that in 3D. As I mentioned earlier, during our thermoplastic welding discussion, destructive testing is part of our quality control program. But this also reinforces what I said about the weld seam being the strongest part of the material. Here you can see a 3-profile rectangular section, and the red box represents the sample, coupon sample that was taken out of it. We turned that vertical, put it in a tensile strength test machine, and applied 900 PSI to it. You can see the weld at the top there and the weld at the bottom, and then the profile section between it. As we would expect, the profile section is the first thing to fail under that pressure, and that confirms that our welds are strong and then is in line with our quality control program. That same destructive testing is then used to validate our structural design methodology and can be shared with clients when required to validate quality control and quality of the material they're receiving on the project site. So to wrap it up here today, I'll briefly cover our live full-scale load test, something that at Uponor we're very excited to have completed. It gives us the ability to effectively design below-ground Weholite modular structures under heavy vehicular loads and shallow cover applications. Most stormwater projects, whether it's a Weholite modular sand filter or underground Weholite modular detention structure, would be in shallow cover situations under parking lots. It's just how those projects tend to work out, or under a roadway. And therefore, we designed our system and tested our system under shallow cover under vehicular load. Here you can see a snapshot of one increment of testing that as it was occurring in the field. Better photo for you to take a look at here is the structure itself. You can see existing subgrade preparation, base material. If you recall back to the Candy slide, you see your non-select fill in that larger angular hatch pattern to the outside of the structure. And you can also see your select fill zone immediately around the structure. And this particular structure only has 2.5 feet of fill over it. So what we refer to as a shallow cover application. We're not really getting a whole lot of mitigating effect of the soil to mitigate that HS25 or CL625 load. The soil really is almost transferring that load almost directly to the top of the structure. And we see that as the critical to design consideration. As the structure gets deeper, the angle of proposed of soil is going to distribute that live load. We're not going to get as big an impact of the live load on top of structure. It's also important to note that this live load testing was conducted on an unreinforced structure. We didn't put any reinforcement in the angular space. It's just a Weholite modular structure with some corner welds and reinforcement in the corners using polyethylene, but no steel reinforcement, no other reinforcement on the exterior of the structure. To run the test, we had a number of data points that we needed to gather to calibrate our structural design in both Candy and Inventor. On the outside of the system, we use pressure sensors to allow us to determine the pressure in the soil and how the soil pressure and how it was reacting to not only the dead load and the live load, but if it was changing over time and coming to some homeostasis. And so the pressure sensors at increments up the side of the structure. We also had strain gauges that were positioned immediately under the the vehicular loads or the axle load from above. And then we used a LiDAR scan on the interior of the structure. As we brought backfill up, we would scan the structure in increments to determine it was performing, the amount of deflection that was taking place inside the structure, and then we can use that to calibrate our Candy and our 3D modeling. Here you can see a snapshot of the structure being picked and set in the field. Here you can see a snapshot of the pressure sensors on the exterior of the structure, and then also the strain gauges are under these black flaps. The strain gauges need to be protected during the backfill process. As I mentioned earlier, ASTM D2321 is the standard for buried pipe installation, for flexible polyethylene pipe installation. It's the guideline that has been adhered to for many years and defines subgrade preparation, backfill selection, compaction placement, and means and methods. Although this is not a buried pipe, that standard is tried and true, so we use portions of the ASTM standard to develop standards for Weholite modulars, particularly as it relates to subgrade preparation and bearing, and then the fill zones around the structure are very similar to what is defined under ASTM D2321. And that's where we have what we refer to as a non-select Zone B backfill, which is a Class 3 material. A wider bandwidth of material is acceptable there. It does need to be free draining, however, it can have some clays and other materials and fines in it. And it also is compacted to 90% modified proctor. Then we have our Zone A material, which is our higher quality select angular type of fill. Most folks might know the nomenclature, 57 stone, 27A. This is a Class 1 or Class 2 type of fill material in Zone A, also compacted to north of 90% modified proctor. For those not familiar with ASTM 2321, it is available, and you can look up the Zone A and Zone B backfill, or the Class 1, 2, and 3 backfill conditions, or you can just ask us and we'll share that information with you for any given project. It's important to understand backfill is a critical component for a buried Weholite modular structure. We extended the backfill envelope 3 feet outside the structure. The critical backfill envelope is 3 feet outside the structure in all directions, and that's where that Class 1 or Class 2 material is utilized. And then outside of that was your non-select high-quality material, but not as high quality as this critical backfill zone. Here you can see them placing and compacting the material and even lifts around the structure using walk-behind hand tampers. We don't want large equipment to compact right up next to the structures because the vibratory loads may impact the design or deflection of the system. So as is common for most buried polyethylene structures or other flexible type materials, you don't use large rollers or sheet foot rollers right up next to the structure. You use smaller walk-behind vibratory compactors. Here you can see them applying some water to the backfill as it's being brought up over the top of the structure. We ran nuclear penetrometer tests at every lift on every side of the structure to determine moisture content and compaction that was also correlated to our laboratory modified proctors that we had run on the material. And so we validated the compaction. And then those actual compaction levels, moisture content levels, also triaxial shear, are then used to calibrate our Candy modeling and our 3D FEA modeling and validate our structural design approach. Here you can see that finishing off the backfill process and then bringing the vehicular load in. We brought the vehicular load in increments of 1/3 of the full 32,000-pound vehicular access load. The way we achieved that access load was we had a steel bin positioned over the rear axle, as you can see here, and down the road from the site was an aggregate facility that also had a weigh scale that would allow us to weigh the back axle. So we simply fill up that bin with enough aggregate to get the axle load to the increment required, up to 32,000 pounds. Then we bring it to our location, we park it over the system, and we run our LiDAR scan, mark our point for pressure and strain, and allow the load to be applied for about a 15-minute total period of time to determine the deflection of the system and how the system performs. At the end of the day, here you can see a snapshot of our external LiDAR scan and then our internal LiDAR scan, along with some of the wiring and other equipment inside the structure. And we're happy to report that at the end of our full-scale load test, our deflections for an unreinforced Weholite modular system under vehicular load were an order of magnitude less than our modeling had predicted prior to the development of the empirical data. So the system is much more robust, and we concluded, just at surface level that our design methodology was ultra-conservative, and the results in the field were much better than anticipated. And we now have the ability to refine our modeling and make the structure a little bit more cost-effective based on this modeling. So before we hand it off to Grant for any questions, I'd just like to reinforce some of the points we made earlier regarding the advantages of the system. Weholite modular, again, 100% polyethylene system, durable, immune to pH, hydrogen sulfide, corrosion, 100-year design life in the face of those constituents. Completely versatile system that allows us to custom fabricate to meet the needs of any project. We have the support and resources necessary to help engineers and owners develop a system to meet their needs on any given project. It can provide a 100% watertight system with both factory and field quality control to ensure that system is achieved. Installation can be sped up significantly in comparison to concrete. A fraction of the time, we're talking hours or days versus many weeks or months when comparing Weholite modular to concrete. And then we can also significantly reduce the project cost where large-scale structures are concerned, reduce the number of loads, reduce the equipment size and cost, and also reduce the site time, as we said earlier. So some significant advantages to Weholite modular. And then the applications where we can use it are virtually infinite. Anything where the treatment or pumping of storage of water is required. As we discussed today, sand filtration, media filtration, gets a higher level of removal and does not lock your clients into a proprietary media system. We have the resources to support engineers with developing Weholite modular sand filter designs to meet their jurisdictional requirements and regulatory needs. And with that, I will hand it off to Grant to answer any questions. Thank you for your time today.
Great, Brian. I really appreciate that. I guess we've had a couple of questions come through. Here we have, just going through a couple of these questions, one is how do you account for buoyancy if I'm burying a unit below ground or below a water table? Brian,
okay. Yeah, we should have included a little bit on that, although it comes up frequently. It's a good question. Essentially, the way we counteract buoyancy is we'll extend the base plate of the wheel panel outside face of structure to capture more soil load to counteract the buoyant force. However, there's a limitation on how wide we can ship, typically around 14 feet, where it starts to become less than cost-effective, and it's time-consuming to ship larger structures as well. So when our width of panel or buoyancy anchor exceeds 14 feet, then we would cast a simple 12-inch thick rebar-reinforced collar around the perimeter of the structure, and the toe of the structure would lock into that. So that would be our buoyancy countermeasure. So when we can, we'll use the wheel panel to counteract buoyancy. When shipping limitations prevent that from being cost-effective, we'll design a cast-in-place collar to go around the base of the structure, typically 12 inches thick, and extend it a few feet outside face of structure to capture the soil column.
Perfect. Another question. We have about 20 questions here. I think we only have time for one more. But how do you compare the cost of HDPE to concrete stormwater systems?
Well, yeah, it's a good question. It really comes down to size. So for smaller scale, 4 foot by 4 foot, simple box structures, we're not going to be cost effective in that range. Those are smaller scale, locally sourced structures. When we get to larger scale structures, like say with a sand filter that would be 40 feet by 10 by 10, we're typically much more cost effective than concrete structures. So it's a scaling factor. At the really small sizes, we're not cost effective. Material to material, however, we are more sustainable and long-term costs are reduced. But from a material-to-material only perspective, with respect to concrete, as they get larger in size, we are more cost-effective versus concrete.
Excellent. Well, I think that concludes our presentation today on Weholite Modular. I thank everyone for attending. And if you have any questions, I believe this will be archived later on, but we'll still be able to answer your questions at a future date should you provide them or forward them on to us.
Thank you, Grant. On behalf of Penwell Corporation, I'd like to thank both of today's speakers, Grant Thornley and Brian McGuire, as well as our sponsor, Uponor Infra, for today's presentation. It's hip to be square, new modular rectangular HDPE stormwater management systems. As a reminder, this presentation will be archived within 24 hours and can be accessed from the homepage at waterworld.com. A reminder email will be sent to all registrants with a direct link to the archive. And we thank you again for joining us today and look forward to serving you with future webcasts. This concludes today's presentation.